So last time we talked about kind of the general, so we did a little like finish up discussion, ILC, super fun. Then we kind of did the intro to stochastic optimal control. And then kind of, discussed in general that problem is really, really hard. And we started talking about the LQG problem, which is kind of the simplest case it's a very simple case / it's the hardest case we have, good theory and closed form solutions for. But it actually is extremely useful in practice. And we use a lot of those results all over the place, even on nonlinear systems, right? So it's really, really good to know that stuff. And it also provides a lot of insight even for harder problems. So it's still like it's still a very there's a rich literature on this, and people are still working on the LQG problem. Some of my favorite recent work in the last few years was work from Ben Recht at Berkeley, and a couple of his students did use the LQG problem to analyze model-based versus model-free RL data-driven approaches. And you can, because the problem setting is nice and simple, they were able to prove complexity bounds on these things and get some really, really cool, sharp results on things you might expect RL algorithms to do. So it's still a very relevant thing to study. All right, so today we're going to finish up the LQG story by talking about so last time we kind of showed this result, this whole certainty equivalent separation principle thing, and this idea that you can separate out state estimation from control and design those separately and then hook them together, at least in the linear quadratic Gaussian case. Today, we're going to talk about the other side of that problem, which is optimal estimation. And, you might say this is not control or whatever. I would disagree. I think this is actually so A, in practice, it's always deeply connected to control, right? We always have these things hooked together in practice. B, there's actually this very rich duality theory between state estimation and control. And there's a deep sense in which they're basically two sides of the same coin and almost the same problem. And we'll talk about the end today. It's actually pretty cool, how deep that goes. So today we're gonna talk about that, finish this LQG story and show kind of the full thing all together, and then introduce this duality idea, which goes really deep and is pretty interesting. All right. Any questions about any of that? All right. Yeah.
What is the name of the group?
RL. Yeah. This is Ben Recht, and I want to say the student is, I think, Sarah Dean is her name, who is now assistant professor at Cornell. And send me a message. I can post this stuff, but definitely ping me about it. As some of my favorite stuff from the last couple of years is really good. Okay, cool. So yeah, I would say again, LQG, it's simple setting, but it's really important because it's simple enough that we can actually do a lot of theoretical analysis and prove things in this setting. So it's a really good sort of playground for control theory, learning theory, whatever. And even if it's not super realistic, it's still we still can bootstrap off of that, and gives you a lot of insight into more complicated stuff. And the algorithms you get there are still super useful because we approximate lots of other things as these things, right? So yeah, it's good stuff to know about, and it's always good to sort of ground your thinking there, even in more complicated settings, to sort of sanity check stuff. Okay, so to recap from last time, we talked about these kind of closely related ideas of certainty equivalence and separation principle. And the idea is, you can sort of design an LQR controller as if it were a deterministic problem, design a state estimator that spits out some kind of optimal state estimate, hook them together, take that optimal state estimate, shove it into the LQR controller as if it were the true state. And that's the optimal thing. And basically, that's the best you can do. You get a bit higher cost, which we kind of showed last time. You can just calculate based on the noise, and that's it. This doesn't hold in general, but we still basically always do it. So this is frequently applied in practice on nonlinear systems. And sort of a rough heuristic on like when this is okay to do is, which we'll talk about in a minute. So we kind of talked about last time how you end up with a state distribution, right? So you no longer have a state X, you have like P of X, right? Given the measurements. And roughly speaking, you can do this separation stuff as long as that distribution is unimodal. And you kind of just pick the peak of the distribution or something like this, right? As soon as your distribution becomes bimodal, basically you don't know where you are. And so things get really sketchy. And so what I would argue is like, if you're in that scenario, the practical engineering answer is to put more sensors on your system so that your estimation problem's easier and you get a unimodal distribution, and then you can do this again. You probably don't want to be dealing with a multimodal state distribution. That is very scary. Okay, cool. So let's sort of now dig into we talked about the control side, and there's just LQR. Let's talk about this optimal state estimation thing, the other half of the problem. So who's like studied or implemented a Kalman filter before? I guess like a lot of you. Sweet. Okay, this is good. So we'll go fast, and I'm hoping like I can just kind of point out some maybe some new little nuggets then. That's cool. Okay, so the first question is, what should I try to optimize? I say optimal state estimation. What does optimal mean? And here's kind of I'll draw a picture and then. So we talked about how, right, you've got this like, say, conditional distribution over your state. So let's draw something like, okay, in one dimension, this is X, P of X. Let's say we've got some funky looking distribution like this, maybe. What is my state estimate in this situation? Like, what should I pick? I don't have thoughts. What's optimal? What's a good like metric for being optimal here? Yeah, so maybe the peak of the distribution. Okay, so that's a reasonable choice. So that would be like here, maybe. Like that's, perfectly defensible choice of like thing. So I would do that, pick that point, throw that into my controller. Okay. But if it happened that I was at the other peak, maybe, things could go badly, right? So this is called the MAP estimate. That stands for maximum a posteriori. It just means maximum of the distribution, right? Okay, so there's another one that's also super common, which is basically the minimum squared error estimate. So like roughly the weighted mean of this guy, which is probably somewhere over here in this picture, right? Something like this. This is called the minimum mean squared error estimate. Okay, so these are just two options. I could make up lots of other things. These are probably the most common two that you'll see in practice, right? So let's write down what these things are mathematically, maybe. So first, the map one is maybe the easiest to write down. So this is maximum a posteriori. And this is, kind of what we said. It's literally just argmax of P of X given Y. And this is, what we said last time. This is probability distribution of the state conditioned on the measurements, which we might say, given measurements. Cool. So that's the peak of the distribution, right? Totally reasonable. The other one, this MMSE thing, is a little bit different. And there's actually, I'm going to write this out because there's an important little trick in here that we're going to use that's kind of fun. minimum mean squared error, MMSE. Okay, so what's this guy? So this would be something like argmin over x. Oh yeah, so this is, okay, so we're gonna do x hat. That's the estimate we're trying to find. And it's this expectation, x minus x hat transpose x minus x hat. So in this expectation, this is an expectation over x, right? Over all x. So I'm integrating over all x. I'm trying to find the x hat that minimizes this guy. So this is the squared error, right? So x minus x hat is the error. I square that. That's a scalar, right? Scalar function. I'm minimizing that thing. Is that clear to everybody? Okay, cool. So yeah, you would also call this least squares, right? Or minimum variance would be another name for this. And that seems perfectly reasonable. I'm going to rewrite this in a couple of ways because we're going to use a tweaked version of this. And also, this is a really good math trick to know about. So the thing, and there's a scalar. So I can rewrite that trivially, like so. So I can wrap the thing inside it in a trace. The thing inside is a scalar already, so this trace does nothing so far. But there's a rule for traces that I'm going to now exploit. So it turns out inside a trace, you can permute the ordering of the stuff inside. So if I have a bunch of matrices inside a trace, I can like cyclically permute the order. So in here, it's just two things. I can flip the order. So in particular, and that's allowed, I get the same answer. Has anyone heard of this before? Some people nodding heads. Okay. So I can do this. And now, what's the thing inside the trace? It's the covariance matrix. Cool. So, all right, so that's fun. And today we're going to write covariance as capital sigma because I'm going to need to use P for the LQR Hessian also later. So we'll do sigma for covariance, P for us to go. And now trace and expectation are both linear operators. So I can flip the order of those. So the next move is I do that and I get trace outside and expectation inside. And now this is very clearly, that expectation inside the trace is now very clearly the covariance matrix. So this becomes just trace of big sigma. So we did a bunch of this manipulating. Basically what it says is minimum mean squared error, least squares, all these things. I can write that down, that least squares objective. That is equivalent to minimizing the trace of the covariance. And that kind of makes sense, right? Because like if I think about what the covariance is, the diagonal of that thing are like the squared errors in each element. So if I sum that diagonal, I'm getting sum of squared errors, right? So that all kind of checks out least squares. Has anyone seen this result before? A couple people. So this little trick I played of like reordering, I call this the trace trick. And like this shows up in a lot of places in like filtering stuff. I use it. I call it the trace trick. I haven't heard it called anything else. So has anyone heard a different name for this? I don't know. That's what I call it. So whatever, we'll call it that. There might be another name for it, but I haven't heard anything else. Cool. It's a fun result. It's kind of useful. Okay, so the final punchline, and we're going to use that later, which is why I did it in painstaking detail. Okay, so the fun thing that we're going to now exploit too is a lot of nice things happen in this like LQG case. One of them is in the Gaussian case. If I have a Gaussian distribution, what happens to these two estimates, MAP and MMSE? They're the same, right? Because it's unimodal, the peak and the MMSE are it's symmetric and unimodal. So like they're the same thing. Cool. So it means we can derive, you can actually derive the Kalman filter several completely different ways. You'll get the same answer. Turns out you can go through a map derivation of the Kalman filter or an MMSE derivation, and you'll get the same exact thing at the end. And there's multiple perspectives on this and stuff. So that's worth knowing. Cool. So that's fun. All right, everyone good on that stuff? All right. So now we're gonna do the Kalman filter thing. And yeah, I don't know. This is one of those this is a classic in the field, right? So I feel like even if you've seen this before, it's good to see it a few times in your life and see it derived a couple different ways. It's good stuff in there. It's one of the absolute key ideas that you should know about and stuff. And it's worth having another look at it always. So we're going to derive this as a recursive linear MMSE estimator. And we're going to, each of those words, recursive linear MMSE, we're going to exploit those in the derivation. And I'm going to there's a sort of fast cheating way to get to the answer here, where I'm going to make those assumptions and just it becomes easier. So, okay, so here's what we're going to do. The setup here, we're going to first lean in on that recursive word. So by recursive, what we mean is I'm going to assume I have an estimate of the state at time k that includes all measurement data up to the current time. Okay, so that we're going to write down, there's going to be some notation here. So we're going to write that as x hat, which is mean k, expected value. And we're going to write it with the following notation. So k given k. That means it's x hat k, it's the estimate at time k, given all measurements, all y's up to time k. So we're going to use that shorthand notation to mean, if I wrote that out rigorously, it'd be the following thing. Expected value of xk given the y's from time 1 through time k. There's another way to write that. So we're going to use that notation on the left. Okay, cool. So we're going to assume we have that. And we're going to also assume that we have the error covariance on that guy. And so in order to do this, you need to bootstrap with these things. And in general, you're just going to make them up. So you need an initial guess at your state and then some initial sort of guess at what the uncertainty in that initial state is. And so this guy, we're going to write this the same way. So big sigma k given k, right? So it's sigma k given all the y's from time k, from time 1 up to time k. And if we were to write this out, sort of more verbosely, it would be this. Okay, cool. And so the idea here, so this is the recursive part. We assume we are given those things. And what we want to do is come up with an update on both of these guys. If we get a new measurement, y at time k plus 1. So the recursive things, I want to be able to just update these guys with one new measurement at one new time without having to resolve the entire back history, right? And there's actually a very long history of this sort of thing, right? Linearly squares, recursively squares, that sort of, this is coming from that lineage that predates the Kalman filter idea. Okay, so we're gonna do that, and we're gonna break this thing down into 2 steps, this update procedure. Okay, so the first one is the prediction step. So here we go. We're going to take we're going to compute a state prediction, which is going to be xk plus 1 given k. So that's the prediction part, right? So this is what we think the state is at time k plus 1, but we haven't incorporated a new measurement yet. So that's why it's k plus 1 given k. And if I were to write this out in detail, this is the expectation, and I'm going to plug in my noisy dynamics from last time. So this is and so if I have xk given k, I just plug it into the dynamics, right? So I got the following thing. And I've got my noise on there from last time, remember? And then this is all conditioned on y1 to k. And so if I kind of just take a look at that real quick, and I think about the noise and all this good stuff, remember, by definition, WK is 0 mean. And this whole thing's linear, so I can pick this apart term by term. So expectation of W is 0 mean. Expectation of BU, well, that's not a stochastic, that's not a probability. That is a deterministic quantity. Like the U is not, a stochastic thing. And then the X is just expectation of AX, and it's linear. A is linear, so I can pull the A out. So it's just A times expectation of X, right? So this, if I were to like kind of, summarize all that, I get out at the end of the day just this. Right, so I just basically get that expectation of xk given y1 through k multiplied by a, and then the BU term, and then the W term is 0 mean, so it goes away. So that's easy enough. So the prediction on the state is I just plug the old state into the dynamics, and as if they were deterministic. And then we also want to update the covariance. So we're going to have same kind of deal over here, k plus 1 given k. And I'm going to just compute the same sort of expectation, but now for the covariance version. So I'm just going to plug the dynamics in. So from the definition, we've got this. And now I'm just going to kind of expand this out by plugging in the dynamics. So it's a little involved, but it's all kind of very straightforward stuff. If you just write this stuff down and think about what it's going to do. So we're going to use the same sort of tricks as last time. So I guess I'll finish writing this out. Okay, this times itself transposed, right? Okay, so if I think about this, remember, these things are all getting multiplied by the same thing on the other side. But did this freeze? Ah, damn it. Apparently. Oh, wow. Wasn't the iPad. It was the whole laptop again. Whole laptop wrecked. Fun. Sorry, guys. Anyone have a good joke? we're back. Sorry, things crashed. Okay, here we go. So based on that, we're going to go ahead and start crossing some stuff out. So in particular, this BU stuff goes away because these get subtracted right there. And then the like AXWK, cross terms are going to go to 0 like last time, right? So I'm going to cross out a bunch of that stuff. And now I'll simplify this down and I'm going to pull out, in particular here, I'm going to pull out the A's because it's linear operator. So if I do that, I'm going to end up with the following thing. And I'll pull out the only noise term that doesn't go away. So this very closely mirrors the whole LQG thing we did last time, which is a theme. Okay, so now that I did that and separated this out, there's two terms. There's a basically deterministic, flavored term. This one, which is just sigma k given k. So, and then this term, which is just the covariance on the noise, the process noise. So this is just big W from last time. So in summary, after all that, what you end up doing is basically this matrix sandwich on the covariance. So it's just taking the original covariance matrix, and this is just kind of propagating that covariance through the linear dynamics. And then we add on a process noise term. So that makes complete sense, right? Basically kind of is the covariance version of the noisy linear dynamics, right? Okay, so that's that. So I'm done now. I predicted the state and I predicted the covariance. That's easy. Next part is the measurement update. This part's a little trickier. But still, like, there's no like kind of super surprising things in here if you think about what's going on. So we're going to do the minimum mean squared error thing, but I'm going to sort of define some machinery first. So first, we're going to define this thing called the innovation. And the idea here is this is the difference between your prediction and the actual measurement. So if I'm going to call this thing Z, so ZK plus 1, and it's the actual measurement, so this is YK plus 1, minus your prediction of what the measurement should be. And so in particular, remember I have this measurement model Y equals C of X, C times X. So it's C times the predicted state. And the reason we're going to spend some time defining this thing is that this is, at the end of the day, this is the thing we're going to do feedback on to update our state estimate. This is basically the thing that this quantity like directly expresses your, say, surprise in your measurement, right? This is the amount your actual measurement deviated from what you expected. And so that's what you do. It's the error signal, right, for the filter. Okay, and then if I expand this out a little bit, you can write this as C of X. So if I knew the real state, right, this would be the following thing. This is my linear measurement model. So it's Cx plus the noise, the measurement noise. And then this is kind of this guy's same thing. Cool, so that's that. And now I'm going to write down the covariance of this guy. So what we call the innovation covariance. And I'm going to just plug that thing into the definition of covariance for this thing. So we're going to call this S. So SK plus 1. It's, by definition, it's this thing. And I'm just going to plug in the definition of Z from right up above that I just wrote down. And then do the usual sort of simplifications. So this is CXK plus 1 plus VK plus 1 minus C times X hat K plus 1 given K. And same stuff repeated, right? And so if I kind of do this again, we're going to play the uncorrelated game again. and cancel a bunch of stuff out. And in this case, the things that we're going to say are uncorrelated are VK plus 1, the noise you sample at time K plus 1, and XK plus 1, right? So the sensor noise at that time, nothing to do with the state. This is an assumption, right? You could, for sure, in some real life systems, have correlated noise where the noise you're getting from your sensor depends on your robot state. It's entirely possible for this to happen, right? But in this case, this is one of the key assumptions behind the Kalman filter. So I don't know, you should know about the assumptions because sometimes they're wrong. And maybe this will bite you sometime, but that's what we're going to assume. So we've got VK plus 1 and XK plus 1 are uncorrelated. And so given that, we can throw out a bunch of stuff and get this SK plus 1 thing to look like the following. And we can pull the C's out. So we get C times this stuff same stuff again. C transpose, and then a noise term. And if we look at that and recognize what these things are, the first term is just the predicted covariance mapped through the measurement model. So this is sigma K plus 1 given K. And the second term is just the measurement noise covariance, big V. Okay, so to summarize then, this innovation covariance thing is just this matrix sandwich with the state covariance mapped through the measurement model plus the measurement noise, what you expect, right? Okay, and then the reason we did this and define this whole thing is this is the thing that we feed back into the estimator. Okay, so let's talk about now the final piece, which is kind of the trickiest piece to derive, but there's a straightforward way to do this, as long as you're willing to tolerate a tiny bit of hand waving. And I'll show you where the hand waving happens. And if you want to do that part yourself, you're welcome to. Okay, so here's what happens. So we're gonna leverage another part of the set of words that I mentioned at the beginning that are all assumptions of this thing. So we did recursive. We already kind of see where all the linear, this is part of that linear thing is going to show up now. So we're going to assume linear feedback on the innovations. So our X hat with the measurement update in it, we're going to assume that it's the prediction plus a linear feedback term. And so in general, there's some linear gain matrix, L, times that innovation. And this L is called the Kalman gain. So we're going to assume that that's what it looks like. And that's basically the most general form of linear update you could do. So now the only question is, what is L? And we'll get there in a sec. So we're going to assume that's the update on the state. Oh, I messed that up. This is state update. And then we're going to now say, okay, if I update the state like that, what should the covariance update be? And it's kind of the same thing we've been doing again, where we're going to smush this into some expectations and simplify it down. So this is going to be sigma K plus 1 given K plus 1. And by definition, it is that this expectation. We've got XK plus 1, and then X hat K plus 1 given K plus 1 times same stuff transposed. And now we're just going to plug in that update thing and a bunch of definitions and simplify some stuff down. And this is going to be Okay, so we got xk plus 1 minus, plugging in the update equation, xk plus 1 given k minus Kalman gain times the innovation. And I'm going to plug in the definition of the innovation. So there's kind of a lot in here. Okay, so I smush all this together, times itself. Okay, now we play our uncorrelated game again. So we've got vk plus 1 and xk plus 1 are uncorrelated. And I'm going to do the usual tricks, right? And I can simplify this down a whole bunch. And it's not hard. It's the same stuff we've been doing. And out pops following. Okay, so that's a covariance update. Has anyone seen that equation before? Has anyone seen that written a different way before? Probably. So there's a bunch of mathematically equivalent ways to write this down. This one is called the Joseph form. And this is the right one to use, I would argue. There's other versions of this that are simpler maybe and that have fewer terms, but they're not symmetric. And there's versions of this that are not symmetric in the way they're written and that also have like minus signs that show up in them. And it turns out those versions under floating point round off error and stuff can produce covariance matrices that are not symmetric and positive definite. This one, because it's symmetric and you're adding two terms that are symmetric, is guaranteed to produce at least positive semi-definite symmetric answer. So under like kind of floating point errors and stuff, this one's the better one to use. Fun fact, but you'll see it written different ways. Just like we saw this sort of the LQR equations written in a couple different ways. Okay.
Is this actually numerically stable or is it just less numerically unstable?
The Riccati equation is numerically unstable. We'll get into this. Yeah, I guess. So the naive Kalman filter equations as written are not great in terms of numerical stability. There are many, many hacks to fix them up. But in this case, it's sort of benign and it's sort of fine. But yeah, this one is better than the not symmetric options. There are even better options with regard to numerical stability if you care. So if you're going to write like a sort of industrial strength Kalman filter to use on a robot and it has to work, you know, if it's on a car and it needs to work every time, guaranteed, and it can't blow up and whatever, there's some other tricks to play. In particular, kind of the most bulletproof versions of these are the so-called square root form. So if you've heard of like square root Kalman filter, square root information filter, the gist is instead of forming this covariance matrix like this, you do everything, you can rewrite all these equations in terms of the square root of the covariance matrix or information matrix, which is the inverse of the covariance. And when I say square root, I mean like basically Cholesky factor. And it turns out those those have even better numerical properties. And because it's the square root, you don't care if it's symmetric anymore or positive definite anymore, because when you square it, it's got to be symmetric and at least positive semi-definite, right? So it turns out those are even better. And if you need it to really, really be bulletproof in a sort of industrial strength kind of way, if you're building a real deployed system, that's what you should do. If you care about this, I'll post, there's a really good blog from, it's called An Uncommon Lab. It's this guy who like is a consultant and writes these things for a living. Actually, I think last I checked or talked to him, he worked for Zipline, actually. If you guys have heard of Zipline, cool company. They were just in the news recently. So the guy who writes their filters has a blog. It's called An Uncommon Lab. And he has like this 3-part blog on like basically all of the practical like street knowledge tips and tricks for doing like real deal in the wild Kalman filters, like all the stuff that you won't learn in like a textbook or, you know, so like square root tricks, like all these like what are they called? Like there's many tricks. Information form, like how to check if your things are biased. What else? There's a bunch of extra little tricks you can put in to sort of like make sure your covariance doesn't get too small and mess your filter up. There's this set of tricks called consider covariance tricks. There's like a whole library of things in there that are kind of like the sort of battle tested stuff that you should do in a real implementation.
What's his name?
Tucker McClure, I think is the guy's name. And yeah, an uncommon line. I'll post this. Someone remind me if I don't do it, and I'll post it to Piazza. His labs, his blog posts are really good on this stuff. It's like this like treasure trove of like hardcore, you know, sort of like practical engineer stuff that again you wouldn't get in a class on this stuff. Okay, cool. So that's the covariance update. The last piece of the puzzle is the Kalman gain. And this is now we're going to invoke one of our other things. So we did recursive, we did linear, and now we're going to play the MMSE card. So we're going to say, you know, we want the MMSE update. What does that actually mean? It means we're going to minimize the trace of sigma k plus 1 given k plus 1 or whatever, right? So we're going to minimize this thing. And we already said this is equivalent to minimizing the trace of the covariance. So
Those be k plus 1s.
yeah, I mean, yes. Yeah, they should all be k plus 1s. It's just annoying to write this extra crap. So I don't know, sorry. Okay, so we want to minimize this x k plus 1 minus x hat k plus 1 given k plus 1 transpose times itself. This is equal to trace of sigma k plus 1 given k plus 1. That makes sense, right? That's the definition. So we're going to minimize that thing as a function of the gain. So I'm gonna go back to my expression, like literally this guy right here. It's got sigma k plus 1. This is this gives me the new covariance. Yeah, that's a really bad sigma. It looks like a Z. So this equation right here, right? It's sigma k plus 1 given k plus 1 as a function of L and some other stuff, right? Question, how does L, what kind of function is this as a function of L, right? So just look at this as an equation. It's got like sigma equals some function of L, right? So what kind of function of L is it? Quadratic function of L, right? It turns out it's quadratic and it's convex in L. So it's basically a quadratic function in L. So if I take the derivative of this thing with respect to L, I'm going to get a linear function of L. And like I set that gradient equal to 0. And that's the answer, right? Because it's convex, blah, blah, blah. So I'm just going to do that. That is it. It's like, it's that easy. It's a little weird because these are matrices and stuff. So if you're willing to tolerate that hand waviness, it's all good. If you don't want to tolerate my hand waviness, the way to really write this down is with the Cron-Vec tricks that we talked about when we did DDP. So what you really do implicitly here is you vectorize both sides and you take the derivative of like vec of sigma with respect to vec of L, right? And that's totally legit. And you know how to do that using all the tricks. That's messy and annoying, and I'm not going to do it here. But if you care enough to go do it, this is how you do it. So we're partial trace of sigma k plus 1 given k plus 1 with respect to L k plus 1. And we're going to set this thing equal to 0 and solve for L k plus 1. And again, it's really easy. But, you know, if you want to be legit about it, you either have to write down some tensor stuff or use the Cron-Vec tricks. But at the end of the day, you get the following thing. Okay, that is the punchline. So I don't know. There's lots of ways to get at this. If you really care about this stuff, there's my favorite. The original paper by Kalman is actually awesome, and derives all this geometrically, which is like beautiful and amazing. And there's a textbook by Thomas Kyleth called Linear Estimation. That's one of my favorite books that also like does the geometric derivation. That's super slick. So you can actually like basically draw a bunch of pictures and like get this result geometrically, which is super cool and beautiful. There's many ways to get at this, but if you care, those are like really worth checking out. Like the original Kalman paper is pretty awesome, actually. And that book by Thomas Kyleth is one of the most beautiful books on any topic, I would say. It's really good. Okay, so to summarize the whole thing. So first you start with a prior, basically. So like x hat, say, at time 0, an initial sigma at time 0, and say your noise covariances on everything. That's the building blocks you kind of need to do this. Then you're going to predict using the stuff we derived for the predictions. So you're going to get, x hat k plus 1 given k. You basically just plug everything into the dynamics. And also I did this for LTI dynamics, but it works obviously with LTV dynamics. It doesn't matter, right? You can put subscripts on the A's and B's. That's all fine. You can also incidentally put subscripts on the noise. So you can have time varying W and V as well, if you want to, although we don't typically do that. Maybe it makes sense. You can have, noise as functions of exogenous variables, actually. So like one sort of example of this where you might want to have time varying noise is say like your noise on your IMU is a function of temperature, which is actually not crazy. That's just like people have done this. If you have like a temperature sensor and like you can have a lookup table for like, V is a function of temperature and plug that in real time. That's a real thing. Yeah. Yeah. So we'll talk about this in a sec. That's a whole thing. So let's do this first and then we'll talk about that. Yeah, so there's the extended Kalman filter, which is the stock move, which is literally, as we've said many times, if you can get away with linearizing, do it. So the EKF is that applied to this. You just linearize about your current state estimate and do this. So you linearize your nonlinear dynamics, get an A and B, and apply this. And it generally works okay. And that's the standard thing, but there's a whole literature on like nonlinear extensions, right? So there's the unscented Kalman filter, there's iterated Kalman filters, there's particle filters, there are Gaussian mixture filters, there's like an insane, literature, but the most basic idea is the extended Kalman filter, and that is the first thing to try. And if that works for you, then do that. Okay, so we do this, then we calculate the innovation and its covariance. The other thing that's worth mentioning is it's totally possible here and often done in practice that you might have different sensors that are asynchronous, right? Like I might get an update from a camera at one rate and an update from an IMU at a much higher rate. I might have a bunch of different sensors coming in asynchronously. So it's totally legit to write down several different sensor models. So I have a bunch of different Ys, right? And a bunch of different Cs. And I can run those measurement updates independently, asynchronously at different times. Totally fine. So I might have 3 different sensors. I have 3 different C matrices, 3 different Ys. Can run those, 10 of one of another, different rates, all that doesn't matter. That's all good. And that's super common in practice also. Okay, so there's the innovation covariance. Then I calculate my Kalman gain. So we did that one. L A plus 1 is. No, they can, depends on the rate at which, generally speaking, what you're doing, right? I propagate my state with a prediction, do a measurement update. I propagate my state till the time when the next measurement, basically you need to make sure that the time of your state prediction matches the time that the measurement was made to do the measurement update.
By state, I mean the things that are in the like X. Like,
Yeah, that's what I'm talking about. Yeah. So if I get so the only thing that matters is that the X hat like prediction, so X hat K plus 1 given K, whatever that is, you have to make sure that the time of that X hat prediction matches the time of the measurement, right? So you have to do state predictions appropriately to make sure you're using the correct state prediction at the correct time for a given measurement, right? So if you have different measurements happening at different rates, there's a lot of bookkeeping there. Yeah. Sure, cool. Say one's at 10 hertz and one's at 50 hertz. Yeah, so what I would need to do is run these predictions at 50 hertz for the other one, for the one at 50 hertz. And maybe I could run them at 10 hertz for the other one, whatever. What I would really be doing is I'd run them at 50 hertz and I'd only do the slower one every 5th update or something like this, right? Which is totally fine. But if they were sort of not exactly that, right? If they had some non-integer ratio, I would have to make sure I did the correct amount of prediction off of the last update step to, to match up the times on those measurements. Does that make sense? Yeah, so that's it. And also if I get a bad measurement and I have to throw it out, I can just run more predictions without doing any updates for a while. Like that's legit, so the point is all of this is asynchronous. You can do it kind of however it makes sense. Yeah.
And then confusing the two sensors, are they updating the same state estimate? Or
Yes.
holding independent state
No,
estimate?
same state estimate. You just have to make sure the times line up. If you're going to do a measurement update, you have to use the correct X hat of T, right? So maybe it's more helpful to think about that part in continuous time. Like you can think about it as you have a continuous time ODE for the prediction, and you run that to whatever T you need to correspond to a given measurement when it was made to do a measurement update, right? Yeah.
Is it at all gonna be a problem if any of your given like sub-sensor, your sensor sub-collections does not hold an observable system?
That's totally fine.
As long as this total system is.
That's right. Yeah. So that's kind of the whole point of this is I can make, partial measurements whenever I want. The filter is fusing all that, right?
Right.
So a given measurement at a given time could be, some little tiny, like even scalar measurement. That's definitely not enough to reconstruct the whole state. But this is like sensor fusion. It's
So, right, but like, so if the system is just straight not observable totally,
then
this won't fall apart mathematically.
it will. But so
But
there's,
the calculations will.
you can do this, you can still do these
calculations.
calculations, but what'll happen in the unobservable case,
Yeah.
your covariance will be unbounded. So
Just there.
the covariance will just do this over time and blow up on you. One way to think about it, if you look at these equations, right, basically the measurement update is squashing your state covariance.
Right.
That's what's making your covariance smaller. The prediction step is growing the covariance. So it's not observable. Basically, one way to think about that is you're not getting enough measurements, or your measurements aren't spanning the full state space. So in some dimensions, that covariance from the prediction step is just growing
Sure.
due to process noise.
There's an unstable mode to the.
Yeah, you can think about it that way if you like. Yeah. Cool.
And here we're not assuming that it's a union model, right? Like,
We are. Yeah. You're assuming linear everything, linear measurement model, linear dynamics model, and Gaussian noise everywhere. So you are very much assuming that you're assuming the underlying statistics are Gaussian here. And practically, this works fine as long as it's unimodal, as long as it's kind of Gaussian.
so noise is a Gaussian, even excess and everything is Gaussian.
Everything's Gaussian here. Yeah, because a Gaussian distribution propagated through a linear transformation state is Gaussian. That's why this works. Actually, that's a deep thing that I should have probably mentioned earlier. That's why this works. And the math for that is like, when I take that expectation for the covariance matrix, if I put a linear dynamics in there, it's all linear. So I can pull the A's out and you just get covariance mapped through the A's in that matrix sandwich thing. That's the result, that Gaussian stays Gaussian. Yeah. So that's it. So yeah, Gaussian stay Gaussian under linear transformations, Gaussian noise, Gaussian prior, linear dynamics, linear measurements. Every distribution in here is Gaussian. So that's like a key thing. But practically, like basically you just need it to be unimodal and kind of Gaussian looking, right? and it's generally okay. Yeah,
Is there a common variant from multimodal data? You just have to measure that?
that's scary. So practically speaking, yeah, there's particle filters are the thing to do in that case. If you have truly multimodal statistics, you need some way of capturing that underlying distribution, basically. And so particle filters are kind of the stock way. There are other ways. Another method that's, if you kind of know something about the underlying distribution, say it's bimodal and you know that, there are other ways to go. So a good way to go in that sort of scenario, if you know a little more, is a so-called Gaussian mixture model filter or blob filter, these are sometimes called. So literally what that looks like is you say, I know there's two modes. I'm going to initialize basically two EKFs, each one with a Gaussian, and I'm going to mix them together. So I have two Gaussian modes that I'm explicitly trying to track with two filters, and you can kind of glue those two filters together in smart ways to do this. So that's a thing too. But yeah, if you know nothing about the distribution, if it's extremely gross and whatever, like particle filters, basically the throw up your hands and just use lots of samples to try to capture the statistics, right? That said, like, if you're a robot, like if you're a car or something, and you have a multimodal distribution over like where you are or something, this is absolutely terrifying and like really, really bad, right? So the practical engineering answer there is you need more sensors to get yourself down to a unimodal situation where these ideas work again. Because there are legit scenarios in robotics though, where you do have multimodal distributions. Usually those are sort of like crazy GPS denied navigation scenarios where you're like using like, vision and stuff like this and like trying to do, feature-based localization. And you basically like say, oh, I see these features. I see these on the map in like several places. You're like, okay, based on what I can see right now with my, sensors and based on the map, I could be here or here or here. And I don't have enough data yet to know which of those is right. That's a legit scenario for a particle filter where you would basically assign probability over the map and you might be in 3 different places. But then as you move around and collect more data, you sort of start to coalesce around. So that's a real application for this that does get used in practice. So there are situations where you have to do it. But I would say in general, if you're trying to like, know where your robot is or whatever your state of your thing, like if you really don't know and it's like this kind of multimodal blob, you're in deep trouble and you probably need more sensors. Okay, so do that. Update. And then covariance update, and then you're done. And then you kind of just repeat. Okay, that is the recipe. Let's see, should we do this stuff? Let's go do this. We'll do the code and then we'll write some more commentary. Oh, right, that's right. My computer blew up on me. So now I have to restart everything. Which means I have to recompile the Julia notebook, which means this is very annoying. Okay. Will it work? Will it work? I think it's going to work. Okay. Hopefully not like painfully slow. A little slow. The JIT thing is annoying sometimes. Okay, cool. So waiting for packages to compile. Right. So this is going to be a really, really trivial example of like a double integrator. So like the sliding brick in 1D. We're going to put some, so these are the dynamics, right? We've seen these already. And then noise. So we're going to put white noise force input on the system. That's what that is. And then white noise on the position measurements. We're going to have position measurements, no velocity. And we're going to put white noise forces on the brick. So it's basically a random walk process, right, is what we've got. So this is 10 seconds simulation. I don't know, the usual stuff. 10 hertz or something like this. We're going to put an LQR controller on here. So we're doing the LQG thing. We're going to have LQR controller, Kalman filter, hook them together. Here's the LQR thing. This is stuff we've seen, right? Making up some weights, nothing big deal there. Cost function. We're going to compute the infinite horizon constant LQR gain for this guy using the control toolbox. We've seen that before, right? Initial conditions, I'm going to just make some up, start at a meter away from the origin or something. And now I also have to initialize the filter, right? So we said, I'm just going to make this up, right? So I'm going to make some identity covariance over the state, and I'm going to initialize it with the state at the origin. So the guess is wrong by a meter or whatever, right? Cool. So this is just setting up the simulation, whatever. So we're going to run this thing. So I'm going to kind of bootstrap this and write the first time step and then put it in a loop. But so I'm going to generate a measurement. So this is a noisy measurement where I take the true state, plug it through my C matrix, and then add noise. And this, by the way, this is how you sample Gaussian noise. So RANDN is samples from a Gaussian with identity covariance. If I needed to have covariance V, it turns out as if you need to do this, the move is you take the sample from the zero mean identity covariance Gaussian, you add on, you multiply it by the square root of your covariance matrix. That's the rule, right? Which is basically like, that's the standard deviation, right? And that has the same units as the things. That kind of makes sense, right? And in general, in the multivariate case, this is a matrix square root. So something like a Cholesky factorization. And then you add on the mean if it's not zero mean. Cool. So that's that. So that's our measurement. We're going to compute the innovation. So note it, that's the X hat, right? Innovation covariance, just like we wrote down. Kalman gain, just like we wrote down. Then we're going to do our state update, covariance update. We're going to plug that into we're going to plug our X hat, our state estimate, into the controller, like we said, certainty equivalent. And then we're going to simulate this with the true state, the control I just calculated using the estimate, and then add noise to it because it's stochastic dynamics, right? So that's the whole thing. Any questions about that? Cool. And now I'm just going to loop that for whatever n steps. We do the whole thing. We'll plot this. Okay, so the blue is the truth, right? And the orange is the estimate. So you can see everything's noisy, right? But it's sort of tracking, doing roughly the right thing. Makes sense. I mean, I can run this a bunch of times, right? It's stochastic. I'll get different answers every time. It's noisy, but it does the right thing more or less, right? Cool. So fun fact, turns out if I go and plot the covariance, the elements of the covariance matrix here, what happens? They converge to steady state values. That's interesting. So in this case, the reason this is happening is this is a linear time invariant system. So the A's and C's are all the same. And so everything's constant. It turns out, like we're going to talk about this in a sec, this is foreshadowing. This looks extremely like the LQR problem. So just like you saw the cost to go Hessian and the Kalman gain converge to constants in the LTI setting, there was this infinite horizon value. Same thing happens here. There's an infinite horizon value for the Kalman gain that it'll converge to in forward time now instead of backward time. So let's go ahead and try that. So I'm going to take the last L at the end of this, right, where it's converged, and I'm going to rerun that whole simulation with the constant gain instead of the time varying gain. And so now that really simplifies the filter. So in particular, I'm just doing linear feedback on the innovations. I don't have to actually keep track of or calculate the covariances anywhere. I don't have to calculate the Kalman gains anywhere, right? So look, now it's just X hat. I compute the innovation, I multiply by L, and I keep track of my X hat. That's all I got to do. There's no more covariance. There's no more gain calculations. That's the whole loop. And let's see what that does. So notice it's a lot worse in the beginning. Why is it a lot worse in the beginning? But basically by the end, it's doing about the same. And this is a new run with new noise and everything, so it's different. But this part is consistent. It's way worse at the beginning, but by the end of this, it's doing well. And so this is kind of that infinite horizon thing. The reason it's so bad in the beginning, look at what's happening in the beginning. The beginning is where this big transient happens. And that's because I have a big uncertainty at the beginning. When I have high state uncertainty, my gain's bigger. Here, I took this steady state gain that was, for out here, where my uncertainty was a lot less. And I applied it at the beginning where there was this big transient. So I'm doing poorly at the beginning. But as long as, I don't blow up by, a few seconds in, I'm basically doing just as well as the old filter. So I don't know, fun fact. Okay, any questions about this? Anyone want to try anything weird?
So when we use there, we get A and P.
Yeah, so that was the LQR controller, to be clear.
So we are not using the K from there.
We are. We're using the K in the controller. There's a controller and a filter here.
But we are using K using B as well, not K. They're like,
So these are, I didn't use the P for anything, I guess. Yeah, so I could have commented out this line. We're not using this for anything. I'm just using the K matrix. I don't know why I did that, actually. I didn't need the P for anything.
you make the noise 10 times.
Yeah, sure. Where is that? There we go. Which one? Process noise, measurement noise? Both? Okay. Why not? Yeah, I mean, it'll still work, it's just really noisy. Are you satisfied? Cool. All right, so let's make some more. If everyone's cool, you can play with this all you want to. I'll post this as usual. Let me make some final kind of comments and notes, and also hint at some really cool other threads to check out. So that's the Kalman filter story, and the LQG story. Do this example, and now let's talk about some things. So first off, addressing the question that came up. How do we do this on nonlinear systems? So the first and most basic thing to try is the extended Kalman filter, which is literally, it's the same idea as, applying LQR to a nonlinear system, right? You linearize it about where you're at, and you just proceed with the stuff we just did. So you linearize about X hat, your best guess, and proceed. Incidentally, the EKF is sometimes called the Kalman-Schmidt filter. And Schmidt was a guy who worked at NASA Ames Research Center during the Apollo program. The EKF was literally invented to navigate to the moon during Apollo. And it was the Kalman filter had only been invented a couple of years before and was not yet widely known. There's a whole other fun story about this where Kalman couldn't get the paper published in like an EE journal or whatever. It ended up getting published in ASME, like the mechanical engineering journal, because the EE journals, I think IEEE like rejected the paper. But it was like not well known. It had only been invented a few years earlier. And Schmidt was working on the navigation, stuff for Apollo, and like he had to solve this problem. The story is he basically like went home on a Friday, like somehow found out about the Kalman paper, and like the original Kalman paper, right, which was like the theory derivation for the linear case. He came up with the EKF idea and like wrote it out and came in on Monday with the answer, and they flew it on Apollo. That was like the story. It was like a weekend, like, kind of thing. It's kind of crazy. And so, yeah, that's the EKF. Many other generalizations of this, as I mentioned before. Okay, now here's the so that you've probably heard of these things, right? There's a lot of that stuff. The fun part that I want to make sure we mention before we end today, which is super cool, and maybe who's heard of this idea of duality between estimation and control? Oh, not too many. Okay, this is good then. So you might have heard of this idea of the Kalman filter being dual to the LQR controller. That's a very cool idea. I kind of hinted at this in the example. So it turns out that there's this very, very close relationship between state estimation and optimal control. That's it goes really deep. And so here's kind of one way to look at this. This sort of MMSE estimation problem that we just looked at. Is equivalent to an optimal control problem that I'll write down right now. So we're going to write down our kind of standard trajectory optimization thing. But I'm going to replace U with W, and it'll become clear what's going on in a second. So our usual quadratic type costing, but maybe a little different. So here's my measurement equation, right? So G is my measurement equation, and Y is my actual measurements, right? That's my measurement noise. Okay, and then I have a cost on the W's here. And I have a dynamics constraint. Okay, cool. So here's what's going on. So let's look at the dynamics first. So those are my nonlinear dynamics, whatever, or they can be linear dynamics. Basically, I make the process noise the controls for my control problem. And that's my like f of x, k, uk now, right? Looks like a control problem. This guy looks exactly like my quadratic control cost in LQR, right? It's like U transpose RU. It's just that, oh, I should have a 1/2 on there, I guess. My R matrix becomes the inverse covariance on my process noise. But this looks like my control cost. And then this guy looks like a state cost. And then this guy's my measurement model, right? So in the LQG case, like G equals C of X, and that all kind of smushes down and becomes a quadratic cost, just like in LQR. The other thing's already quadratic. The dynamics are linear, just like LQR. So this is, in the linear case, this is an LQR problem. And I can like take this exact setup and solve it like using Riccati. And it turns out I get a Riccati equation. It is the Kalman filter, right? So this is like kind of wild. It turns out if I go solve this with dynamic programming in the linear case, I get the Kalman filter exactly. And all those Kalman filter equations we wrote down, like the update equations for the covariance and everything, turns out is exactly the Riccati equation. That Joseph form update on sigma is exactly the same equation that shows up for basically sigma looks like the Costigo-Hessian in LQR. There's this like mapping between the two, and they're exactly equivalent. There's some really interesting like equivalent stuff that shows up. Basically, LQR, you're propagating backwards in time from a terminal value of P. Here, you're propagating forward in time with an initial value of sigma. So they're like time reversed, which is kind of interesting, but there's this like really deep connection between these two things, and they look extremely similar. But even in the nonlinear case, this is the estimation problem, right? So even in the nonlinear case, you've got this like, you can rewrite the estimation problem as an optimal control problem. And there's like a very deep set of connections there. One thing that like maybe if you've done filtering before, you might not have seen, or maybe you have, if I basically I can also do the estimator version of MPC. I can solve this problem directly with a batch of measurements. I can do what's called a receding horizon estimator. So I can take a batch of past measurements and do like a sliding window on them and solve this nonlinear optimization problem directly. This is sometimes calling a moving horizon estimator or sliding window estimator. People do this in SLAM sometimes. Kind of cool. Yeah, there's lots of interesting stuff in there. It's very deep. I think, yeah. That's our measurement model. So let me write this down, actually. This is a general nonlinear measurement model. So like we talked about for us, so let me write this. So if f of x equals ax and g of x equals c times x, this is an LQR problem. So what this is just, the g of x is just a nonlinear measurement model. So in our case, it's linear, it's c times x, right? It's the one we did, but you can in general, obviously have a nonlinear measurement function, right? For different sensors, cameras, whatever, right? And then, yeah, so if I take this optimal control problem and solve it with dynamic programming, like we did with LQR, you get out the Kalman filter again. Okay. I think that's it for the day.